And if I don't hear back from you, maybe you failed. It just reassigns it to somebody else. So the master will just keep giving out pieces of work. Do this, do this, do this. And then it has some kind of a timer. If you haven't finished it on time, I'll just ask somebody else to do it. And eventually I'll get all the pieces done. So the worker is sending a heartbeat back, and if it's silent for too long, it figures it's crashed and just reassigns it. And as it's taking the work and pushing it across the machines, it doesn't have to worry about where the data is. It doesn't have to say, well, I better give this job to that machine because the data's there. No, all the data is readable from all the nodes. And this is another feature of, because it never updates a file, it never has to lock a file. So you can always read a file. There's never a case where you can, like a Windows or a Linux file system where somebody's about to do an update. They lock the file, do an update, and then they release the lock. While that file is locked, nobody can do anything. Well, this file system never locks. It just keeps writing at the end, writing at the end. And MapReduce is network and rack aware. So it's a pretty complex piece of software. But when it places jobs and when it places storage, it is literally so in one of these big computer centers, you'll have, let's say, 10 racks here with 20 machines in each one of them. And then you'll probably have like 2 Ethernet connecting all the machines, all coming up to a pair of duplicate switches. And when it says, okay, I'm going to assign the next piece of work, or I'm going to put a piece of storage somewhere, it knows it doesn't do any good at all to put a piece of work on one computer and then put a replica on another computer if it's in the same rack, because if this rack loses power, you've lost 2 computers at once. So it's smart enough to say, oh, I got to be in a different rack, and oh, by the way, they can't all be tied to the same network switch, because if I lose the network switch, I would lose them all. So all that's built into it. Okay, so now let's talk about MapReduce. This is a good example, exit polling. So the idea of exit polling, if you're not aware of it, is on the day like today when they're voting in New York, they typically, I think by law now, you're not really supposed to ask people who they voted for, because they're not supposed to like bias the election as it's happening. But they are allowed to ask them questions about, like, did you care about global warming when you voted? Or did you believe that the schools should all teach the Bible or evolution or whatever it is, okay? I think this one's actually asking the vote results. So the idea is you have somebody asking questions, all right? So you have a voting place, and you have multiple mappers and multiple reducers all running in parallel. And the results for one age group is not influenced by the results of another age group, so they can be processed in parallel. So what you're going to do is, you're going to have somebody, they're the sorter mapper. They're going to be asking questions. How old are you? How old are you? And then once you answer, they're going to direct you to another human or another computer that says, oh, I'll process all the ones that are 20-year-olds. These are for the 30s and these are for the 40s, right? And then the reducer person takes the subset of data and asks, how did you vote? How did you vote? How did you vote? So instead of all of these 3 reducers like looking at all the data and having to keep track of how old they are and then have all the mixed data to get the answer, you're basically pre-processing the data in one dimension. You're saying, as I assign the work, I'm already splitting it up in one dimension, which is by age. And then that's mapping. Then you reduce the data. In this case, we're reducing in 3 different reductions based on age. This is reducing the data for the 20-year-olds, for the 30-year-olds, and the 40-year-olds. Does that make any sense? So here's another diagram. So you have node 1 and node 2 and node 3. And they're pulling in data and they're running some analysis, they're running some algorithm to basically map the data. They're saying this piece of data should go to this node, or this node. So all 3 of these nodes are looking at a stream of data and they're just dividing it up and they're partitioning it. Now in this case, it shows them partitioning the data in some cases to themselves. But the way to think of it is, let's say that the exit polling goes on for 3 hours. These guys are running in pure map mode. They're just pushing the data and separating it. Then the election's over, you use the same 3 nodes and say, okay, now you run the reduction. And that's typically what happens, is you run map, where you're filtering and pushing the data out into a very particular pattern. And then the reducers are like just running sums and totals and averages on their sub-piece of the data. So you can use exactly the same nodes you used in the mapping phase on the reduction phase. So mappers map input key value pairs to some intermediate key value pair. So in effect, you're bringing in raw data with key values, and then you're directing some subsets of keys, like everybody in the 20s or everybody whose name starts with A or B or C. You're transforming them into intermediate records, in effect, under another key, which would be, these are all the A people and those are all the B people. Output pairs do not have to be the same type as input pairs. Given input pair may map to 0 or many output pairs. Output pairs are collected with calls to contact right radical pair. So what they're saying is a piece of input data might actually satisfy 2 or 3 conditions, and it may be written out to multiple sets. Because what you're doing is you're taking a big set of data and you're mapping it to other subsets of data. And one piece of data, you may be trying to calculate by age who's voting, by sex who's voting, by political party who's voting. So one record comes in, might get written out to the Republican subset, and to the female subset, and to the age 20 group subset. Application can use the counter reported statistics. I have no idea what that means.
Kurt, is mapping and indexing, would that be synonymous, or are they 2 very different functions?
I view indexing as assigning an index, whereas mapping, I say, is creating a collection based on an index. So if they already got an index that says, I'm a Democrat as opposed to Republican, I'm going to write you in that file. I'm going to write in that file all Republicans, and that file all the Democrats. And I'm using the index to figure out which subcategory to map you into. So then the outputs of the mappers are sorted, and then they're partitioned into reducers. The total number of partitions is the same as the number of reduced tasks for the job. In other words, if you partitioned all the data into just Democrats or Republicans, then you only have 2 reduced tasks: reduce the data for the Democrats and reduce the Republican data. Now, you can split the reduction job of the Democrats across 25 computers, and then you have an accumulator that will take the results of those 25 and accumulate the answers. And that's where you get into specifying a combiner, so you can do intermediate aggregations. The intermediate sorted outputs are always stored as a key length, key value, length value format. Key length, key value. Is there a comma there?
Key length, key, value length, value.
Oh, yeah, thank you. Key length, key, value length, value format. Okay, thank you. So now, once you've split the data across into these subsets, you've mapped it, then you reduce it, and they're going to be operating off a subset that has a shared key, and presumably a more narrow range, like the people between 20 and 29 and the people between 30 and 39. And the reducer implementation pass for the job. So each reducer goes through 3 phases. It shuffles, it sorts, and it reduces. The input to the reducer is the sorted output of the mappers. In this phase, the framework fetches the relevant partition of the output to all mappers. Framework groups reducer inputs by keys. Same key at this stage is shuffle, sort phase. Fetch there being merged. I don't remember this. I have a diagram for this. That's used by, no. All right, I gotta figure this out again. So I think what it's saying is, in the shuffle phase, the mappers are splitting it up into subsets. And then the system, the Hadoop system, is taking subsets of the shuffles and assigning it. So like if you split it up into all Republicans and all Democrats, it's not going to stick all Republicans and all Democrats on just 2 machines. It's going to take all the Republicans and it's going to shuffle chunks of the data across 25 computers each, so that you can go on and do the sort on 5 machines faster. So you're shuffling and sorting constantly. And I don't know. And then in the last phase, after you've got it all shuffled and then all sorted within that, then you run whatever calculation you're going to run, and then that's called the reduce. And this can literally be an answer. It can be like 16, or it could be a whole bunch of data, depending on how you set it up. Application of reported statistics. I still don't know what that means. They claim this is how Obama won his election. Dodd-Frank measures its compliance, blah, blah, blah. Anyhow. So Amazon and Microsoft this is actually the older generation, because these are like the freestanding machines I was talking about a minute ago, where like these are the racks and these are the blades. I think they're almost always now delivered in trailers, so they can assemble them and test them in Texas, drive them up here and turn them on, instead of shipping them up here, wiring and drying them. Anyhow, in the big clusters like Amazon and Microsoft, these servers can be used for anything. You know, you can get time on that one, or you can buy 16 racks and do what you want. But also, they offer machines that are already up and running Hadoop. So you can push your data up there and then push up a Hadoop application. And why this is really important is, if you want to do something where you want to make the analysis really quick, you want to have thousands of computers. But maybe only once a month you want to do that. So you don't want to buy thousands of computers and have them sitting there doing nothing. and then at the end of the month, fire them up, do your calculation, and then let them sit there, right? So what you're getting is like time sharing on these big Amazon and Microsoft clusters now. There are literally millions of jobs, Hadoop and everything else, are constantly coming into these machines and leaving these machines. So at any one moment, you can say, I need a cluster of 1,000 machines. And the system automatically allocates 1,000 machines to you, puts a Hadoop framework on it, you run your Hadoop calculation for an hour, and then the machines go back into the pool, and you only pay for an hour's worth of time. So this is yet again why the economics of this is in favor of this being used more and more and more. So is NoSQL better than SQL? It is massively scalable. It is highly available because it has the built-in redundancy if you go with the triply replicated, and it is lower cost. It's predictably elastic. You know, it's like when you're buying a car for your family and it's just you and a spouse, and then all of a sudden you have 2 kids, and then you have 4 kids, and then you have 8 kids. Like, you can't like stretch the car, right? You have to keep trading in the car and buying a new car. That's another nice thing about these models is if the workload is big, you just add a couple more cheap computers. If it's small, you just use a few. It has limited query capability. The data comes in a funny way, and you can ask some questions and it processes it nicely. If you ask other questions, it is just painfully slow because you're trying to read across the way the data is not laid out. It lives under this thing called eventual consistency, which means, I think we talked about this before, the data is sort of almost always right almost all the time, but it's never absolutely right all the time. Because, for instance, if the data is split across 3 disks and you ask, what is the value of something, you might be getting it off of disk 2 exactly when disk 3 is being updated with the latest purchase, okay? So you're going to think that that store only sold 715 candy bars when actually they sold 719 because one of them was being written just as you read it. But the nature of the data to use here, you never care. You're always looking for aggregate data and trends and things like that. You don't care about specific pieces of data. So you want to put payroll on there. I don't know, non-standardized, so portability is an issue. Maybe to say it a little more positively, SQL is really highly standardized now, and you can take your Microsoft SQL and throw it away and buy Oracle and run your applications pretty quickly. I suspect this stuff has kind of settled down into some pretty common things. I don't think that's a fair criticism. Insufficient access control. Yeah, I wouldn't want to put one of these on a public network. These are always on a back-end network behind your front-facing. Your front-facing machines are taking orders and doing business, and you're pulling data off of that and loading these machines, and you would never put these on a public network. What time did we start, at 3?
Mhm.
How come nobody said break?
We just let you go.
Huh?
We just on a rant, I let you.
I think what I'm going to do is finish this off, and then we'll pick it up and start actually trying to run jobs and really get our fingers dirty on Friday.
Thursday.
Okay. So are you familiar with this concept of ACID? I don't know if they teach this in like programming 210 or whatever the databases is. This is a very formal computer science kind of a concept, and one of the big advantages of classic SQL is it is ACID. It has these 4 properties, and you really don't get these with Hadoop, but you do with a well-run SQL system.